Welcome. In this video I'm going to show you how you can perform a g-test of goodness of fit, also known as a likelihood ratio test, using RStudio and an R kernel of 4.2, although I think this will also work on lower versions. To show you how this can be done, I first need to load some data, so I'm going to load that in, Control Enter. And the data has, I can actually show quite a lot of different variables and has 1974 rows. This was the General Social Survey from 2012 and I adjusted it slightly here and there for these examples. The field I'm going to be interested in is the marital status, which is labeled MAR1, and just to make a frequency table out of that I can use the table function. And then I can see that, for example, 972 people were opted to be married, or they indicated to be married. Let's put it like that. I will also need the so-called expected count. So in this case, I'm just going to assume that each category was equally likely to be chosen. That would be my hypothesis to some extent. I can then simply say, well, it's going to be the sum of all the frequencies divided by the number of frequencies, and that's then going to be my expected frequency. Alright, then the chi-square values for each category, or for the g value if you want, you simply take the logarithm out of those frequencies and each of them divided by the corresponding expected frequency. So that's what this one is doing. I'm not done yet then. I actually need to multiply each of those then with the frequencies. So I can do this one. And then finally I can see my chi-square values. Now because it does this for each of them. Now the g value, the chi-square value if you will, is then 2 times the sum of all of those. And that's going to be 1137.012. Now the degrees of freedom is the number of categories minus 1. So I'm going to store the number of categories as k and then subtract 1. So that should give me 4, because I had 5 categories minus 1 is indeed 4. I can then use the p chi-square function. Give it the chi-square value or the g value, the degrees of freedom, and I don't want the lower tail, I want actually the right tail. So if I run this, it should give me my significance or p value. This e minus 245 means you need to divide this by 10 to the power of 245, so it's going to be 0 and then 244 zeros and then 718. So very, very small. Below 0.05, which is the usual threshold. So my original frequencies, my original counts are significantly different than if they would have been distributed equally. Now there are also some packages that can do the same thing. For example, the desk tools package has something for this. So I already installed it once, so I only need to load it now. Otherwise you might want to run this install packages. It requires the expected proportion, so that's simply the expected frequencies divided by the sum of all the frequencies, and then you get your expected proportion, in this case 0.2. We then create a vector with the same length as that, so I'm just going to repeat that expected proportion, and then each is going to be the k actually. I could simply remove this and put k there, and that should give me 5 times 0.2. Now for the test, because I've loaded the DeskTools package, I can use the g-test function and give it as x my frequencies and as p my expected proportions. And that gives you then a log likelihood ratio g-test goodness of fit. The g value 1137, which is hopefully the same here as we calculated earlier. The degrees of freedom and the p value. Now you can also use a Williams correction or a Yates correction with this, or actually not the Yates one, only the Williams, because Yates requires 2 data values for this function. RV de Moivre also has this in their library. So if I run this one or load it, I can use the gtest function, feed it my frequencies and the expected proportions, and I should get the same results. In the appendix, I'll go over some corrections that could be applied. That Yates correction, I'm not going to discuss all of that here, but it's possible to do that. And I'll quickly just run it through. Oh, I shouldn't have to do the print. Just need to adjust the frequencies and then calculate that Yates variation. It just calculates the G value or the chi-square value, and you can use the p chi-square to obtain the significance. Williams correction requires a so-called Q value, and this is the formula if you don't have an intrinsic null hypothesis, and you simply then divide your original chi-square value or G value by that Q. And then there's also, oh, this isn't working, chi-square Williams is not found. That's strange because n is not found. Yeah, n is the sum of the frequencies, so n equals the sum of my frequencies. I think I called it my frequency, and now it should work. Sorry about that. And run. Yeah, so now it gives me the result. There's also another Pearson, ES Pearson, different than the Pearson chi-square test version or Pearson, which is simply to divide, multiply the original by n minus 1 and then divide by n, and then you get a slightly different one as well. These two, as you can see here, are slightly different. It's just in the rounding that they appear to be the same result. Right, and that's it. I'll leave a link to my website where you can download this R script if you're interested in the data file that goes with it. And hope this was helpful, and thank you for watching.